This is the first problem from the Unit 9.1 rate law problem set, where you're given a data table with 3 or more trials showing you the concentration of the reactants A and B, and we're trying to figure out what impact those concentrations of reactant A and reactant B have on the rate of the reaction forming products. So as always, you start by setting up the rate law expression, which is equal to the rate, or rate is equal to the constant K times the concentration of A raised to the power M, that's a random letter, times the concentration of reactant B raised to the power of, in this case, we're going to use the letter N. The letters don't really, it's not important which letters you use there. So that's the basic rate law expression. Our job now is to figure out what is the value of M, the exponent M, and what is the value of that exponent N. We're going to start by trying to figure out the value of the exponent M, the effect of the concentration of A on the rate. So if we want to figure out the concentration of A on the rate, we're going to have to find 2 trials where B is constant. So coming over here to the data table, go to reactant B, find 2 trials where B is constant. So we're looking at trial 1 and trial 2 where B is constant. So we're going to look at trial 1 and trial 2 and ignore trial 3 for the moment. And so we are then going to look at A, and we see that trial 1 is a larger number than trial 2, so we're going to have trial 1 be in the numerator. So we are going to have trial 1 over trial 2. That's the plan there because it's bigger. So if we look up the concentration of A from trial 1 divided by the concentration of A from trial 2, we're going to set that equal to the rate from trial 1 divided by the rate of trial 2, remembering that the whole plan is to try to figure out the value of the exponent M. Okay, so what we're going to do is we are going to then plug in, we could use any of the 3 trials, but I always tend to use trial 1. So the concentration of A from trial 1 is 4.0. The concentration of A from trial 2 is 2.0. Okay, remember that's what we're trying to find. The exponent M. Rate from trial 1 is 1.60. Rate from trial 2 is 0.80. I'm not concerned. We're just trying to find the mathematic relationship, so don't worry about units here. Simplifying, we have 2, and over here we have 2. So you can probably see that the exponential value of M has to be 1. So we're going to go ahead and change that M to a 1 up in the rate law expression. So now your job is to do all of this again for reactant B. So reactant B, we need to find where 2 trials of where A is constant. So I see trial 1 and trial 3 where A is constant. So we're going to use trial 1 and trial 3 for B, and trial 1 and trial 3 for the initial rate. So if we take a look, we're going to see that trial 1 is a larger number than trial 3. So we're going to put trial 1 over trial 3 as we figure out the effect of the concentration of B on the rate. So we're going to start with the concentration of B from trial 1 divided by the concentration of B from trial 3. We're going to set that equal to the rate from trial 1 over the rate from trial 3. So substituting numbers in, B from trial 1 is 6.0, from trial 3 is 3.0. Remembering that what we're trying to do is find the value of N. Rate from trial 1 is 1.6, I'm sorry, yeah, that's right. It's 1.60 divided by 0.40. So simplifying, we get 2, and then on the right side of this equation, we're going to have 4. So what we have here is we're trying to figure out the value of n here. This has to be squared. So the exponential value of n is not 1, it's 2. And so that right there is your rate law expression. So we have just done part A, determining the rate law expression. That's what this is right up here. Now skipping to C for a moment, the overall order, that's where you just add up the exponents. So the overall order here for this equation is going to be 3. So that's a pretty straightforward question to come up with. Lastly, we're going to find the rate constant, right? And so to find the rate constant, rearrange the equation for K. So that's going to be the rate over the concentration of A to the first power times the concentration of B to the second power. And then we're just going to use trial 1 to substitute in for the rate and the concentrations of A and B to solve for a mathematical or quantitative answer here. So we're going to see that K is equal to 1.60, and here is where we do want to include units. This is 1.60 moles per liters per minute. So that's all the numerator. The denominator, concentration of A is 4.0 moles per liter to the first power. Concentration of B is 6.0 moles per liter. That's going to be squared. So I'm going to finish my work way over here. So if we just work on the denominator first, so moles per liter per minute up in the numerator, but 4 times 6 times 6 is going to give you 144, and then the unit here is going to be moles cubed divided by liters cubed. Okay, so now we just need to simplify 1.60 divided by 144 is a very small number, 0.011. I think I'm short a significant figure there, but let's focus on figuring out these units. So here, the moles up in this numerator is going to cancel with one of the moles down here. Now, because you have nothing left in that numerator of the numerator, we're going to substitute a 1 in there. And I'm going to choose a different color here. So the liters up here is going to cancel with one of the liters down here. And now it's just a matter of simplifying all this unit. We're going to end up with liters squared over moles squared per minute. So it's liters squared per mole squared per minute. So that is the value of the rate constant. There you go. There's problem set question number 1.